So this is joint work with my advisor, Christos Papadimitriou at Columbia. And the kind of broad problem that we're studying is the problem of learning in games. And I want to my hope is it's a 5-minute talk. I will only kind of give you the big picture of what I hope out of this line of theory and vaguely kind of what sense of what was in this paper. But the broadest way we can say this is what would we love out of a really predictive theory of games, right? And that's kind of one which could tell us something about the possible, strategic combinations of strategies that can occur as the outcome of a strategic interaction. And obviously we're all learning theorists here. So the kind of the learning version of this, which I think is, really the important interpretation is we've got a bunch of agents and they're collectively learning and what can we say about the outcomes that they learn? So I'm going to be studying specifically the replicator dynamic, which for a learning theorist, you guys can just think of as being multiplicative weights with a step size of 0. And I'm not going to go over this because this is a short talk. But the picture we do want is what are these things I'm looking for, right? One version might be convergence to a Nash equilibrium, a picture that looks a bit like this. We sort of converge to some strategy profile that's at an equilibrium. This is not what happens in general. In fact, in general cases, we're going to converge to something that's set-wise. We're going to converge to a set of outcomes, but we would still love to be able to say what that set is and make as strong a statement as we can about what that set is. Specifically, this is in dynamical systems. This is what's called an attractor. I'm kind of going to flash the definition of an attractor on screen that we're using here, but broadly, it's the intuition you have of a set that attracts a nearby set of points. Now, finding attractors in any dynamical system is a hard problem, and game dynamics is kind of no exception, and it's a thing that people have thought about for a long time, and there's progress on, but broadly speaking, the picture is very unknown, especially beyond the cases where we do converge to Nash equilibrium. So I'm going to deviate now and talk about kind of the key conceptual tool that underlies this line of reasoning, which is an object called the preference graph. This is a very natural combinatorial thing that you can pull out of any game, and it comes out kind of naturally. You start with a game like this. You turn each of the strategy profiles like this into nodes in a graph, and then for every strategy profile that differs for just one player, we put an arc indicating the direction of preference for this player. So in this case, the goalie player prefers to go in the same direction as the other player. Okay, and clearly this captures kind of the fundamental combinatorial structure of this game, in some ways more so than the payoff matrix does, which has some additional numbers that we've thrown in there. There's actually a canonical way to add numbers to this as well, which you can weight the arcs by the difference in payoff, the utility gained by deviating. This is a really interesting object in its own right. I spent a lot of time thinking about it. It turns games into diagrams that you can draw and look really nice in talks, and honestly, I think gives you lots of intuition. If there's such a thing as a theme in this lightning talk, it's that this graph tells us lots of interesting things about games beyond learning, but I think especially about learning. The sync equilibrium is the other concept I want to say here, and it's literally just the sync connected components. It's the generalization of a sync. If a sync existed, it would be a Nash equilibrium. And so a few years ago, there was this suggestion in this paper that we don't know how to compute attractors of the replicator dynamic, but we do have this graph and it kind of looks like a good approximation. And its sync equilibria maybe form a good kind of proxy method for these attractors. And in an out paper 3 years ago, there was this result that said that actually every attractor of the replicator dynamic, which is sort of viewed as this abstract sort of blue thing that we don't know where it is, this circle actually contains this entirely combinatorial object that is the sync equilibrium. And actually, in the follow-up work and the subsequent alts, we showed that in zero-sum games, this correspondence is exact. The sync is giving us all of the information. And so we were kind of left with this conjecture, it seemed too good to be true, and it is, that the sync equilibria might exactly define the attractors of the replicator dynamic, despite having thrown away most of the information of the game. Or at least that they might be in one-to-one correspondence, right? We only established that one contains the other, Now, I'll just kind of summarize what this paper did in my remaining few seconds, which is we sort of proved that both of these conjectures are wrong, and we did it in kind of a combinatorial way by building in some extra arcs into the graph, and then I end up with all these lovely Tix diagrams of increasing complexity, showing you, yeah, look at that. but the kind of the moral of the story is that actually like you can get a sufficient condition about like when this is not possible and the conjecture is restored. And it's also kind of graphical in nature, which is you sort of forbid a few of these corner cases. But like the broad takeaway I kind of want to leave people with, okay, so these are all the cases we really can identify where the attractors are and where they are graphical in nature. What I want you to be sort of left with is like, okay, the picture is more complicated than just the sync equilibria. We need something a little bit more than that. On the other hand, it's somehow not that much more complicated. Like this graph and these sinks are really close to whatever the total answer is. And it does seem to have some kind of combinatorial structure, even if we haven't like nailed down exactly what that looks like. I'm very hopeful. I think it's a super interesting problem. I think any progress we make on this will be like really interesting. And I think there's lots of interesting ideas floating around with it. So anyway, thanks. If you have any questions. Yeah.
Okay, about 3 minutes. So, okay, I don't have time to full screen this, so you have to see it in preview. But this is my paper, Group Realizable Multi-Group Learning by Minimizing Empirical Risk. I am told that Matus lovingly presented this as a poem. I have no such literary ambitions here. I have some slides in preview. Good. So what am I studying? So the problem setup here is a problem setup called multi-group learning, which in my opinion is like quite natural generalization of path learning in the sense that here I introduce just a new character, a collection of groups, which are just subsets of the input space. And importantly, these could be potentially intersecting in many ways, and also potentially infinite with like say finite VC dimension. So the question is just how well could we learn on all of these groups simultaneously, right? How well could I find one classifier that does well with respect to the best thing on each group simultaneously? Okay, and then here's like, the color's a little bit washed out, but here's a half space. But if I kind of judge my half space, not just overall, which I think this is the best half space if I did this right, it's not doing very well on this group over here, this kind of vertical red group over here. It's doing actually no better than 50%, right? So I really want one thing that does well with respect to everything simultaneously, or the best thing to do on every group simultaneously. And a natural definition for this is the following. Okay, so this is the agnostic kind of definition of this, right? I want to do with as well as the best hypothesis on each group, conditional on each group. Okay, so this is a group conditional error rate. By conditional, I literally mean like conditioning on that group in the sense of conditional probability. And I want to find one classifier that does well with respect to each group. So obviously, kind of one thing that you see immediately is that this must be improper. I cannot just pluck out a good hypothesis because they're different on every group. And the natural question to ask is like, how does this generalize realizability? So if I actually want the realizability assumption in path learning, right? Regular realizability says I have a perfect classifier overall, right? Group realizability is a weaker condition that says on every group, I have a perfect classifier that gives me all my labels, right? So realizability implies this, not vice versa, because they could be different. And my goal is just to find a perfect, or sorry, a good F on every group, one good classifier on every group, right? So ERM over H clearly no longer suffices. So what could you do, right? What you could do is actually what we show in this paper is that I didn't have time to talk about like the concept class that you do ERM over, but there's another concept class that's necessarily larger than H in some way that you could do ERM over. And you actually recover the exact statistical rates that you might expect in the original single group path learning setting, realizability, right? If you're familiar, there's like a log n over n rate in realizable path learning, right? Recover the exact rates that you might expect. And then you could assure this simultaneously for all the groups with high probability. And then the last takeaway is just that we know that in realizable learning, path learning is hard, right? ERM is hard computationally, right? And this is like an artifact of optimization in the sense that like we have to optimize the 0-1 loss. It's also NB hard to do this, but for kind of different reasons that are very particular to the fact that we are optimizing over a bunch of groups simultaneously. I'll just say that even if ERM is easy over H itself, right? Finding this ERM is hard for kind of different reasons that have to do with the group structure. And so that's all I'm going to say. Yeah, so yeah.
Okay. So hello everyone for the 2 o'clock session. I want to say thanks to Matus for graciously offering me chair the session. And I hope you all are refreshed on the lunch break. A lot of nice vegetarian options today. So our first speaker for the session is Qijia, Shenyang, and she's going to be talking about designing algorithms for entropic optimism.
All right, so thanks for being here. So today I'm going to talk about designing algorithms for entropic optimal transport from optimization perspective. There's some.
Just disconnect audio on your laptop.
Okay, so this is way better. So this is doing work with Vishwak, who is a PhD student at MIT. Okay, so to begin, let me set up a stage a little bit and just introduce what optimal transport problem is. And I'm going to explain this using a slightly stylized example. So suppose we have a bunch of warehouse and stores located throughout the city. We're going to call the warehouse location this alpha here. So each of the point denotes the location of the warehouse. And each of this location has alpha I amount of items. And we also have a bunch of stores. So these are denoted by the beta here. And the beta, each of the dots or points is the location for the store. And each of the store has or desires beta j number of goods. And so the goal here is that given this information, we want to come up with a transport plan that reallocate these goods. And so alpha and beta here, you can more or less think of as just two discrete measures in the setting. And so given this problem, it's very natural to ask, it seems like there are many ways to do this transport. Is there in some sense an optimal way of doing so? And so to define optimality, I have to first explain or introduce the notion of a cost. So say the cost of moving an item from location I to location j is Cij. And once we have this cost, it's very natural to sort of write down an optimization problem of the following form. So suppose we have xij items that are moved from location I to location j, then we want to minimize the cost of doing so such that we have two constraints. These are redistribution constraints because we want the items that are moved out of location I to add up to alpha I, and the amount of items that's received at location j to add up to beta j. Right, so here X is a m by n matrix, and so we want to try to minimize the cost with these constraints. And so this is a very sort of simple instantiation of the optimal transport problem in the context of efficient resource distribution. Now, in general, we can also consider continuous distributions alpha and beta. And then with this kind of more general setting, we can write down an analogous optimization problem over the space of distributions. So here, instead of minimizing over the m by n matrix, we are minimizing over the joint distribution or the coupling. This is denoted by pi here. So we want to minimize the cost. This is how we evaluate the cost, subject to the two redistribution constraints. This is just a coupling saying one of the marginal has to be alpha and the other of the marginal has to be beta. Okay, so one comment that I want to make here is that solving this optimization problem not only uncovers an optimal transport plan, but it also delivers a measure of how different the two distributions alpha and beta are. So for those of you who know about Wasserstein distance, this is in fact one way to define the distance. Okay, so even though this problem is ubiquitous and it's kind of elegant, it turns out that solving this OT problem as written is quite inefficient, both for computational and statistical reasons. And this, in some sense, motivated Sinkhorn in 1967 to propose the following regularized objective. So we still have the same constraints, but the objective is slightly changed. And in particular, the change just involves adding a bit of entropic regularization. So epsilon here is a regularization parameter, and this is just the entropy on the joint or the coupling pi here. And with this small change, it gives a faster iterative algorithm for solving this problem, and this is called Sinkhorn algorithm, and essentially reduces to performing alternating projection on the two marginals. And this is also popularized by Marco Couturi in a 2013 paper. Okay, so this is an optimization problem. In particular, it's written in terms of pi and it's constrained. But whenever we have an optimization problem, it always makes sense, or it's always a good idea to check the dual to see if it might give you a slightly different insight on the problem. So if we do that here, we end up with the following objective. This is a dual objective, and it's a maximization problem. It's maximizing over a pair of dual potentials, phi and psi here. And it has sort of these slightly more complicated terms. But the important thing to notice here is that, first of all, this dual formulation does not have any constraints. So that's nice to work with. Second of all, one can also show that this dual objective is jointly concave in terms of phi and psi. And there's also a relationship between the dual potentials and then the primal measure, and it's related this way. So one can always go from one to the other without any loss. Okay, so here we have the dual objective, and so even though this is concave and it's unconstrained, we still have two variables to optimize over, which seems a bit unwieldy. So one thing we can do is just to do a partial max, and this is okay because we have joint convexity. So meaning if I fix a phi and I just work out analytically what's the best psi given this particular phi. So I can do a partial max, and it's actually analytical in this case. And after this explicit partial max, we end up with a semi-dual objective, and it looks something like follows. So now the semi-dual objective J is only a function of phi. And just two comments or two property on this objective. First of all, we don't lose anything by doing this reduction. So it's sufficient to just work with this objective 1 here. Second comment is that the semi-dual objective is actually concave in terms of phi. So it's also nice. So all these properties just suggest that we can simply perform gradient ascent on this semi-dual objective to solve the problem. And so, we can also once we have this gradient ascent idea, we can write out the update a bit more explicitly. And to do this, we can work out the derivative of J. In this case, it's actually closed form. And so suppose we are given the current dual potential phi, we can form the corresponding primal variable, this coupling here by this formula. And it turns out that the derivative of J at this current phi is just the difference, or the beta y, which is the desired y marginal, minus the current y marginal. And this is the derivative of J. And so if we put things together, what semi-dual gradient ascent would do is just at the current iterate, let's say I have phi y, I would update with the step size eta, and then use the gradient, which is the desired marginal y minus the current marginal y. So this is how far are we from satisfying the constraint. And if we compare this update with sinkhorn, there's actually a deep connection. So sinkhorn, there's a dual viewpoint on the sinkhorn, which is instead of using the difference between beta and the current y marginal as the update, we just take the log difference as update. So these actually bear a lot of similarity. Okay, so let's put it side by side, and let's just look at or try to compare these two updates. Well, the first observation is that both of these updates are trying to match the y marginal. So we're trying to match the current y marginal with the beta, which is desired y marginal. The fixed point of both of these iterates are the same. And this is actually sufficient, or at least one can show these are sufficient to make sure that we will converge to the optimal coupling. But the more important observation here is that it seems like there's a more general procedure one can consider, which is instead of matching beta and phi or pi using log, we can just introduce a general mapping, this phi here, and just matching any transformed or any sort of mapped version of beta with a mapped version of the y marginal, and we will call this phi match. So, all of this are somewhat natural, but you might ask, why is it interesting, or what can you say about this? So it turns out that there's a deep connection of this phi match algorithm with mirror descent. So consider this update, phi match update. One can show that in primal space, it corresponds to a minimization problem of the following form. Now, it's not so important you parse everything here, but notice that if this first part, so if this first part is the first variation of a functional f, then this update is actually the same as a mirror descent update in measure space, right? So because this would just be the first order Taylor expansion, at the current y marginal, right? So this would just be the first order Taylor expansion plus some proximity term. Right? So this would just be a mirror descent update. And so I'm not going to go into the proof, but just by using this insight and picking different functional f, we can give a theorem which says the convergence rate is something like 1 over n epsilon. Okay, I think I'm out of time. So there are a few things I haven't talked about, but I think I'll stop here. Thanks.
All right. Hello, everyone. Thank you for that introduction. It's wonderful to see you all and a pleasure to be here. Today, I'm going to tell you about this work, reusing samples in variance reduction. This was a rather fun piece of joint work with a number of current and former students at Stanford that I had the great pleasure of working with. And this project is about a number of, I think, very fundamental to me questions about the understanding, the complexity of solving certain structured learning theoretic problems. And while I'll get to the broader set of results we have in the paper, to start motivating this work, I thought it might be a little easier and straightforward and helpful to start with one motivating example that I think motivates a lot of the works in the paper. And this motivating example is a problem I think many of us are familiar with in one way, shape, or another, and that's the problem of finite sum optimization. So to motivate our work, let's consider this standard setting where we have some n functions, f1 through fn on Rd. These will be convex L-smooth functions. And here we can think of every individual function fi, when evaluated at a point x, as being the loss of this model, some model x on data point I. And our goal will be to optimize some aggregation of our loss functions. We'll consider the standard one of minimizing the average loss. So let capital F just be at a point x, just be the average of the loss functions fi at a data point x, at a model for a model x. And we'll make a standard assumption that f is mu strongly convex. And our goal will be to compute an epsilon approximate minimizer of f, this average loss function. Now, this is a fundamental, very well-studied problem. There have been numerous algorithms. There have also been lower bounds. And at this point, we know, up to polylogarithmic factors, the optimal complexity for solving this problem, at least in terms of the number of gradients of the individual fi that need to be queried to solve the problem. And here I'm going to hide log factors. I'm not going to distinguish between randomized and deterministic algorithms. We'll focus on randomized algorithms. And the optimal complexity for this problem is it's known that you need at least n queries to the gradient of the individual fi, plus something that squares as the geometric mean of, again, the number of loss functions fi, and the ratio of the smoothness to the strong convexity. And this bound is known to be optimal. All right, so given that this is optimal, what are we going to say in this talk? And to motivate our results on the question we study, I want to say a little bit more about where this bound comes from, or at least one way of deriving this result. So one way of obtaining this bound is you can use certain reduction frameworks, things like approximate proximal point or catalyst, that essentially reduce the problem of minimizing f to solving a sequence of regularized subproblems involving f, where instead of minimizing f, you minimize f plus some quadratic regularizer on a point with value regularization amount alpha. And it's known that it suffices through these frameworks to just solve these subproblems square root alpha over mu times. Right? In turn, each of these subproblems can be solved with natural stochastic methods, things like stochastic variance reduced gradient descent, and that solves these subproblems to high accuracy, just using a polylogarithmic number of queries to the full gradient of the average loss function f, as well as L over alpha queries to the individual gradients of the individual loss functions fi. So where the state of the art or optimal bound for this problem comes is just by tuning alpha and noting that a full gradient of f can be computed by n gradients of the individual fi. All right, so with this bound, as you'll note where the optimal bound comes from, it comes from a certain trade-off between the number of gradients of f. These are like full passes over your data set, and then some number of gradient queries or some number of operations involving the individual loss functions fi. So the motivating question for this paper and our work was to study these sorts of trade-offs. We asked, what is the optimal trade-off between the number of gradients of f, this is like full passes over your data set, as well as the number of gradient fi for distinct I. This is like the number of particular data points you might need to look at and compute the gradients of their loss functions at some number of points. So we call this gradient of f in the context of this work a full batch query because it's a full query over the data set, and querying a gradient of fi for an I that you haven't looked at before we call this sample query. All right. Now, using the work I showed on the previous slide, the state-of-the-art bounds, you can interpret that as saying it suffices then to solve the problem with square root alpha over mu full batch queries, as well as square root alpha over mu times L over alpha sample queries. We want square root alpha over mu iterations of the outer loop, and every outer loop requires one full batch query and L over alpha sample queries. So in this context, the natural question motivating a bunch of our results is this trade-off optimal? Like, is this the optimal trade-off between the number of full batch queries and sample queries for solving things like finite sum optimization? Now, you might think, given the optimality of the query complexity I said before for finite sum optimization, you might think this is the optimal trade-off, but perhaps excitingly, we showed the trade-off can be improved. In fact, you can improve the number of sample queries by a factor of square root alpha over mu. In other words, you can think of this as rather than taking L over alpha samples in every iteration, for every subproblem solved, you can reuse and look at the same L over alpha functions in every subproblem you solve from then on. And we essentially get this by arguing that we can reuse a bit of the randomness in the sample queries in solving every subproblems, and thereby save this factor and get better trade-offs. All right. Now, there's a number of reasons you might be interested in such a result or want it. For one, depending on the particular layout of your data or caching behavior or locality, you can imagine there's different trade-offs in the actual computation of computing a full batch query versus querying things like sample queries. And depending on the architecture, something like this might come to a speed up in certain settings. I also think this is just a rather fundamental question about the information theoretic complexity for solving these problems, so it's a natural thing to study. And I'd also want to emphasize that in certain cases, this notion of a sample query, I think, makes a lot of sense. So for example, if you consider the special case of finite sum optimization of regression, you can view a full batch query as matvex involving the matrix A in your regression problem, whereas sample queries correspond to picking a random row of this matrix. And one of, I think the things personally motivating this work was you could ask, what is the optimal trade-off between the number of matvex and random row queries you need to solve regression? And this says that actually the bound you would have gotten by just looking at prior work for that can be improved. All right, so more broadly in this paper, we consider a number of problems beyond just finite sum optimization. More broadly, we consider a number of these sort of variance reduction schemes that use some sort of outer loop, like accelerated proximal point or catalyst, to reduce solving the original optimization or learning theoretic problem you want to solve to solving a sequence of subproblems to high accuracy stochastically. We note that in a number of these settings, this outer loop of reducing to subproblems is robust to small error in perturbing your solutions to the subproblems you output. And then in many of these cases, some of the randomness that's used in solving the subproblems is oblivious to the actual progress you make over iterations. Right? So with this, we show that if you just apply these frameworks, but every iteration when you solve the inner subproblem, you add a little bit of random noise, then you can prove in a number of these cases that you can reuse the randomness in this oblivious randomness in every inner loop, and with that get a savings. This idea of adding a little noise to hide randomness shows up in a variety of literature on dealing with adaptive versus oblivious adversaries, and we use it here. For finite sum optimization, this framework applies because SVRG, when solving the subproblem, simply picks the FI uniformly at random, uses the same distribution no matter what center regularized subproblem you look at, so you can reuse that randomness over the iterations. We analyze our methods by introducing a notion that we call pseudo-independence. This is an analog of pseudo-determinism in analyzing randomized algorithms, and we give a rather general theory and framework for analyzing when you can reuse the randomness by using this notion of pseudo-independence to reason about the dependence of the randomness within the sequence of inner loops. In our paper, we then apply this framework to a number of problems beyond just finite sum optimization. So we apply this also to things like solving Markov decision processes and get new trade-offs between the number of full passes over the input you need, as well as the number of random samples you need of transitions in the model. We also apply it to generalizations of regression called L2L2 matrix games and get improved trade-offs between matvex and random row and column queries. We also apply it to things like top eigenvector. So that's our results in a nutshell. Please check out the paper. We provide this framework very generally in the hopes that it'll apply more generally and people can use it. So please use it. And also check it out because there's a number of other insights along the way in some of these applications I don't have time to get into. For instance, our outer loop reduction framework for MDPs is new to the best of our knowledge. We also apply it to L2, L1 games, which is a problem where some of the randomness in the subproblems is oblivious and some is not. And it has some interesting applications for L2, L2 matrix games. So thank you for your attention. Welcome any questions.
Thank you so much.
Just one question. Can you tell us a little bit about pseudo-independence and also, for instance, how close you can get to proving like a Chernow bound for it?
Yeah, so pseudo-independence, it has to do with kind of quantifying how much the certain outcomes depend on the randomness in certain contexts. And it's just we give some general theorem about pseudo-independence that we use to generically analyze the framework. You could prove the framework directly by reasoning about how the output distribution changes when you reuse the randomness. We use this notation involving pseudo-independence, which seems to be a unifying way of thinking about it and analyzing it. As for your comment of Chernow, an alternative to these algorithms you might try instead would be to argue that the samples you take the subproblem has a type of concentration. You could use it no matter what subproblem you solve. And in some of the applications, we know something like that works, but in some of these applications, we don't, which I think makes the application interesting. Not that I have an impossibility result either, but great question.
So you're talking about reusing samples,
Mm-hmm.
and you have an improvement of square root of some quantity, and it looks like connected to composition theorems and differential privacy.
So this idea of reusing randomness, this idea of like adding a little noise to hide randomness, indeed, it arrives also in differential privacy. In many contexts in the paper, we give more references to the various contexts where it arrives. The factor we're saving here is there's some number of iterations of an outer loop. And naively, every inner loop would take the same number of samples. And we're saying take the same samples you use once and reuse them in all of them. So we pick up a multiplicative factor of the number of subproblems. And that's where that factor comes from. But indeed, that's another place where the same technique has connections. We gave it through this general framework for this problem, these types of problems. Great question.
Hey, thanks for the great talk. Can you say maybe a little bit more about what you mentioned in your last slide about L1, L2 games?
Yeah, so in L1, L2 games, we considered solving them through certain natural stochastic variational inequality solvers. And there in the distribution in L2, L1, some of the samples you're able to draw obliviously. They're picking random entries of the matrix corresponding to their magnitude. And some of it comes from, depends on the current iterate, the simplex side. Depends on the current iterate and is not oblivious to the trajectory the outer loop is following. What we say is in these cases, you can reuse the randomness in the oblivious part, but you have to use fresh randomness for the other part. And that still gives some savings, but a different type of savings. But it's nice that it still applies in this case where there's multiple types of randomness happening in the subproblem solver. But in case someone's concerned, no, we're not saving the dependent one. That's an interesting question of whether there's further improvements possible.
Thank you.
Thanks.
Arun again for the talk.
Again, great question.
Great. Thank you for the introduction. My name is Brian Bullins. I'll be talking about our work on convex optimization with p-norm oracles. Here, this is based on joint work with my wonderful collaborators, Deeksha, Arun, and Arun. So I wanted to start off with some basic techniques in optimization, namely in one that arose in the previous talk, that of the proximal oracle, right? This idea that if we imagine access to an oracle that would provide the minimizer, maybe not of the original function we want to minimize, which of course might be too strong in general, but some regularized version of it. For some regularization parameter lambda queried at some centering point C, that we can ask, if we had access to such a thing, what could we do with this? How useful might this be? And this is fairly well known, right? So in particular, with acceleration, it is known that we can find an epsilon approximate solution for the problem after something like lambda times the diameter of the problem, x star L2 norm squared over epsilon, quantity to the half iterations. For those familiar with accelerator rates or gradient descent, this looks familiar, but if you were to squint and sort of swap out the lambda for the smoothest parameter, and this goes back to Guler, an accelerated version of this earlier work that's unaccelerated, which is of course based on Nesterov acceleration, and we're letting x star denote our minimizer. Right? And this type of tool is useful not only sort of in and of itself, but also in a broad context, including large scale, distributed optimization, non-smooth problems, etc. And there's a really nice monograph by Parikh and Boy that provides more context here. Now, a related oracle, which is maybe more recently introduced and studied, and is sort of an extension in the sense of, a limiting case in the sense of the proximal oracle, is what's known as the ball oracle, in this case specifically a Euclidean ball oracle. And here we're going to have it be parameterized by the lowercase r, which we use to denote the radius of this oracle. And what does the oracle do? It says for some function f that we want to minimize, suppose the oracle would give us, when queried at some centering point c, we're going to sort of imagine things that are exact, the exact minimizer of our function in some ball, L2 ball of radius r around c. And it turns out that this too can be accelerated, and the optimal rates that one can achieve are something like a distance to the minimizer, the diameter of the problem, L2 norm of x star, divided by the radius parameterizing this ball oracle, raised to the 2/3 power, where again our x star is the minimizer. And once again, we have very nice applications in non-smooth, parallel, and stochastic optimization settings, among many, many others. But in both of these cases, we notice an explicit and very particular dependence on the Euclidean norm and how these are defined, particularly in the ball oracle, right? We're considering the ability to minimize in an L2 ball of this radius r around our centering point. And in the case of our prox oracle, right, there the regularizer was defined in terms of the L2 norm and more particularly raised to the basically a square, right? And so we want to consider, right, the key transition we want to offer in this work is asking, well, what would happen if we considered some p-norm generalization? And in the case of our prox oracle additionally, where we allow for some alternative power s instead of 2, right? So it's a very natural augmentation to the oracle for the appropriate parameters, lambda r and s and p. And if we now have these access to these oracles as opposed to, or in addition to the standard proximal oracles and the ball oracle, we can ask what are the rates that we can get provide under such access, and we might further wonder whether or not we can establish that they are optimal in some sense. And so what we do in this work is we provide rates of this form. So we have our standard lambda diameter over epsilon raised to a kind of complicated dependence in terms of P and S, where we further sort of simplify things by denoting this nu as the difference of these two things. So you could plug that in and get a complicated-ish power in terms of S and P. But I will argue in a bit that it's actually quite natural. And we further provide rates of this form for our ball oracle. And in both of these cases, we generalize, sort of extend and generalize the previous results, but to the p greater than 2 setting. Okay? A couple of neat downstream consequences of these techniques. We can use them in the context of LS regression, which is this problem basically just looks like your standard, L2 regression. If S were 2, L infinity regression, modulo the issue of there being a raised to an S power if S were infinity. But now, rather than maybe as it has typically been the case of asking how we might solve problems of this sort by reducing it to a sequence of quadratic quadratic problems, right? So there's the least squares subproblems. We could ask instead what we might be able to do for this problem if we had access to LP regression subproblems, right? Technically, there's a smooth version of it, but the spirit holds. And one would expect, of course, that as P is bigger than 2 and gets closer to S, that the number of queries you would require gets smaller and smaller, though there's a subtlety with the trade-off there. Also interesting here is the ability, based on appropriate generalizations of the techniques, to kind of recover, in a sense, known results for high order optimization, not only in the Euclidean settings, but also in non-Euclidean settings for P greater than 2 under the appropriate smoothness assumptions. And to complement our upper bounds, as weird as the rates might have looked on the previous slide, it turns out that for zero respecting algorithms, that is algorithms that will query in the span of the outputs, that these rates are effectively optimal up to constants. I briefly wanted to highlight what the algorithm looks like. For those familiar with Monteiro-Sveiter acceleration, this should look somewhat familiar, with the main difference being, of course, now the dependence in the sort of primal and dual updates that end up being coupled, depending on or sort of querying the oracle that we require. We call this conceptual because of some weird implicit dependence between the x variables and our parameters or our sort of coefficients lambda. This is, again, sort of a hallmark of this style of acceleration, though we can get rid of this need for the resulting line search in that case by generalizing a type of Monteiro-Sveiter oracle. We call it a generalized Monteiro-Sveiter oracle. And the nice thing here is, while again, the definition looks maybe a bit unwieldy at first, it is quite natural when viewed in the context of proximal oracles for which this this oracle is satisfied when sigma equals 0, right? So the proximal oracle is in a sense kind of the best type of thing to satisfy this, but it can also, the flexibility here allows for accounting for things like high order methods as a consequence. In all of these cases, one might still ask, well, we have these oracles, and that's fine to imagine oracle access, but how do we actually implement these? And that's a problem that requires a lot of additional context. I will provide one way of approaching this in the context of the ball oracle, whereby under an appropriate or under a certain kind of alternative to self-concordance, namely quasi-self-concordance, the upshot of which is a sort of stability of the Hessian, that you can, under such conditions, implement the ball oracle, the p-norm ball oracle, with not too many queries to a linear system solver. Basically, not too many Newton steps suffices to approximately implement an LP ball oracle. So the key takeaways of this talk, we've provided an analyze non-Euclidean proximal and ball oracle methods. And our lower bounds show that for these zero respecting algorithms, our rates are basically optimal. And we've shown some applications of these. I would note there's very nice concurrent independent work by Contreras, Guzman, and Martinez-Rubio that also studies non-Euclidean high order and proximal point methods, and which achieve basically the same types of rates. And in terms of future directions, how we might handle this issue of implementing the oracle efficiently in broader context is one clear open problem for which I think appealing to stochastic methods and other nice techniques of optimization might be promising. And there's also a problem of going between the LP-LS regression reduction, for which we provide some reduction rates, but which don't seem to be optimal. With that, I'll finish. Thank you.
Thanks, Brian, for the talk. Do we have the next speaker can come get set up?
You mentioned a lower bound for span respecting algorithms.
Yeah.
I guess like this is very natural for like gradient methods. but for a proximal oracle, I might evaluate the proximal oracle itself with a lot of gradients. And so like the span of the gradients I evaluated might be much larger than the span of just like the iterates generated from the proximal oracle. Is there like a good intuition on like why span respecting still makes sense, or is like that extension kind of easy?
I would say that if I understand correctly, the lower bound holds in the span respecting sense in a large part by appealing to like a Nemirovsky style construction, right? Which is so it's going to be sort of non-smooth to begin with, and for which there isn't really much information beyond the gradient info. And yet somehow when you have the ability to kind of smooth out the function, roughly speaking, by querying this prox oracle as an augmentation to the original very non-smooth f, that gives you some extra power over, say, just gradient or subgradient queries to the problem, and that will improve, right, as maybe p and or s increase. But that's like it kind of the span respecting the limits of that span respecting method, or the ability to kind of hold in that sense, are sort of they naturally change as s and p and the lambda parameter like also are changing. But it's kind of alternative to just if you only had gradients query access.
Thanks, Brian, again.
Thanks for having me here. Actually, this is my first overall paper. Yeah, and I think I didn't expect it to be award. I think that's really thanks to my brilliant collaborator, Boyao, Li, Tianyu, Minghak, and of course my advisor, Yao Qing. Yeah. So first, let's get to today's topic. This work is actually giving some theoretical explanation to recent empirical observation that is very counterintuitive. So I will give a quick introduction about this background and our core problem. I will give a summary of our main contribution and discuss some limitation and feature extension. Yeah. So first context here is that when you optimize the over permissive neural network, it's typically have a very ill-conditioned loss landscape, which means that if you look at the height of your loss function, you will observe that a few large eigenvalues and a Westbrook of a small eigenvalue, and there will be a very significant gap between those large eigenvalues and the small eigenvalues. This geometry also described as the river valley landscape in recent research. I just plot some previous work figure here to let you more easy to understand the context. And to introduce our core problem, we need to give some definition here. We define the large eigenvector space as the dominant space, and with its corresponding projection matrix. And same for the Brook space, those are the smaller eigenvector space, and also the projection matrix. And a very important property is that there are previous research finds that these two spaces have some kind of invariant property. Yeah. So under the above contents, there is clear work in 2018. Gagwari have a very interesting finding about how SGD's expected gradient align to these two spaces. It define alignment function as the projecting norm proportion to its original norm. They found a very interesting two-phase alignment behavior of SGD. Like the alignment is first decrease initially. It's a very sharp decrease. It will rise, oscillate, and stabilize near value near 1. Yeah. And because in the later phase, he observed that the gradient is mainly aligned to the dominant space. So he made a conclusion that in the later phase of training neural network, your update is mainly happening in dominant space. Yeah. But recent work challenging this view by doing a very easy experiment. this is also a clear work, and they do an experiment that they project the project update to the corresponding subspace and observe. They project the update in corresponding subspace on a very high alignment regime, like when your algorithm is entered to a very high alignment regime. They projected update to corresponding subspace. They found that the dominant projected actually failed to decrease the loss or even increase the loss, while the book projected successfully decreased the loss and agreeing agreeing a loss curve just like the original algorithm. And this is very counterintuitive because your gradient, your expected gradient of SGD, which means the full batch gradient, is actually aligned to the dominant space. But dominant projected actually failed to decrease the loss. Yeah. So the summary of core problem of this phenomenon here is that how does the step size govern the evolution to show two-phase alignment behavior in this ill-conditionless landscape? And the second problem is that why this counterintuitive phenomenon emerge in such setup. So our work is to give a theoretical analysis about this phenomenon to figure out why this happened and how this worked. So this is the setup of our work. We just give a very toy setup about quadratic function, but we consider this in a very high dimensional regime, and those are some regulatory assumptions that to make well-defined this for the stochastic analysis. Yeah, and our SGD is actually gradient descent with a Gaussian noise. Yeah, we can take a look for 5 seconds. Yeah. So back to our core problem. So the summary of our contribution here, the answer to first problem is that how this step size choice have an influence on the alignment dynamic. So actually, we identify two alignment regime. Like if your current alignment lie on different alignment regime, the behavior could be totally different. Like if you lie in a low alignment regime, your typical alignment behavior is actually controlled by the step size. There will exist a critical step size that if your current step size is greater than this critical step size, the typical behavior of your alignment will be increased, and otherwise it will be decreased. But the interesting thing is that in a higher alignment regime, which if your current alignment is very high, alignment is actually self-correcting. Like whatever the step size you choose, the typical behavior of your alignment will be decreased. And I think the most interesting thing here is that if we set the spiritual gap, which is the proportion of the dominates eigenvalue proportion to the book's eigenvalue goes to infinity, both these critical alignment value will goes to 1. Yeah. So in an ill-conditionless landscape, the first alignment regime is the typical alignment, typical behavior. Like you can control the alignment by a critical step size. Yeah. The second contribution is that we give an answer to the problem 2. We first identify a critical step size for both projected method. That if you want one certain projected method to decrease the loss, you must need to let your current step size smaller than this critical step size. We also identify a critical alignment value that split 0 to 1 into 2 regime. if your current alignment is low in the low alignment regime, the critical step size for the dominant projective method is smaller than the critical step size for the book projective method. And it's the other side on if your current alignment is greater than this critical alignment. So why this phenomenon emerge? Because if you are in the low alignment regime, so if your current step size is lie in this it's like in this interval. So you will fail to decrease the loss by a dominant projective method and successfully decrease the loss for projective method, book projective method, and also this critical alignment goes to 1 as the spatial gap goes to infinity. So because the limited time, I just give iteration about the rest part. Like the above theorem is about 1 step, and we also give a long-term analysis, like from 0 to t, and we need additional assumption to make this analysis hold. And because in experiment, we observe the 2-phase alignment behavior. And this is the theory for first phase behavior, like it will keep decreasing. And this time is logarithmic growth with the initialized parameter norm. If your norm get bigger and bigger, and it have a logarithmic growth with the initialized norm. And about the second phase, we give a limit alignment, expected limit alignment about this look complicated. The iteration is that if the spatial gap goes to infinity, this goes to 1. Yeah, and this is some simulation. The setup is just like exactly like our theory setup. With different spatial gap, you can see the alignment is actually stabilized in different positions. And if your gap goes to bigger and bigger, and the alignment actually approach to 1. Yeah. Yeah. Okay. Yeah. I think that's all. And this is some. Yeah, you can see this is some limitation and extension. Yeah. Thank you.
Yes. Thanks so much. Questions?
Yeah.
So the alignment quantity is gradient based, but we don't use gradient methods anymore. We use things like atom. We use steepest descent methods that follow different directions. So is there an alignment property that holds if you replace?
Yeah, that's actually is a very interesting question. Actually, from this research, you can get a iteration that if you only have a gradient, if you only apply a gradient method, you will have a bottleneck to optimize the book direction because the yield condition and the noise effect. So if you have something trick like mirror descent or preconditioning, the direction will have a shift. So you may not have this bottleneck in the later phase. Yeah.
Let's thank and congratulate Shenyang again.
Yeah.